Good afternoon from Dhaka, Bangladesh. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka. And we are organizing a lecture series on AS and A-level chemistry. Today is the 37th lecture on transition metals. So we start with what is transition metals? Well, I have shown this periodic table to you, and I'm sure that you are acquainted with periodic table. But which are the elements we call them transition metals? You see, this is transition metals, this color, these are transition metals. Okay, but we know also in about periodic table that we have S block elements, P block elements, and D block elements, as well as F block elements. So how do you define S block element, P block element, D block element, F block elements? It's simply that when we call S block elements, the outermost shell, that means valence shell, the electron must have S electrons, partially or full-filled electrons. Similarly, P block, the valence electron should be in P orbitals, or partially or fulfilled. D blocks, valence shell should be in D orbitals, partially or fulfilled. And similarly, F blocks, the valence electron should be in F orbital. So D orbitals means that we start from these to this, that is from group 3 to group 12, all are D orbital elements. Okay? But then you see, we have scandium, yttrium, and lanthanum that they are important. They are also called rare earth elements because the properties of transition elements differ with those elements, these three elements. And we will call that our transition elements is from group 4, 5, 6, 7, 8, 9, 10, 11, 12. These are transition elements. Okay, next is that, next slide, we go to next slide. Okay, why we have to read transition elements? Because it is very, very vital to life, and it brings color to our lives. I can say one example where, well, if we do not have iron complex, that is hemoglobin, all animal life will vanish. So it is so important, hemoglobin, which is a complex of iron compound. Here is iron, it's complex of iron compound. So here the entire animal life depends on this. Similarly, the plant life, it's a chlorophyll, which is the living part of the living plant. So chlorophyll is a magnesium complex. Magnesium complex. So we'll come to the complex later. Okay, how we see the electronic configuration? We have discussed this in fourth lecture, how the energy level of different orbitals. We are seeing here the 3s, 3p, 4s, 3d, 4p. Well, subshell 3s, 3p, but then we do have a little bit higher energy of 3d than that of 4s. So we have to take into consideration of 3d and 4s. Moreover, as I say, we will discuss only titanium to zinc as our d orbitals, that is 4d orbitals elements. So how do we do it? Well, you see, we put electron here in 3s level, then we have to put electron while it is filled, then we have to put electron in 3p, and then we cannot put electron in 3d. We have to put electron in 4s. Is it not? Because the energy difference between 3d and 4s, energy level difference. Okay, If you remember, we have shown electronic configuration by SPDF notation, and then simplifying this, that inert gas configuration there, all argon, inert gas configuration, you see that, all argon inert gas configuration. And then we have 4s, 4s2, etc. And this is what the electronic configuration, just to remind you that these are so important to understand 3D subshells electronic configuration. Okay, so when we fill the electron after argon, we fill 4s, not 3D. You see, 4s. So here is 4s. It is electron in boxes. We show it electron in boxes. We have discussed it very details, and I hope anyone in your level will understand this. So similarly, we are coming like this, and then you see the scandium where we have 3D1 electron, and we said that this is what is the transition element. So we just mentioned that titanium to zinc we would call transition elements for 3D level transition. I come back to this periodic table. So I say your syllabus contains only this 3D group 4, the period 4, electronic configuration of this. That means we will discuss titanium and zinc, excluding scandium. We will see why we exclude scandium. We will find it out later. Okay, so you see, we said here, we call this the 10D metals, which electronic configuration is here, and it has got variable oxidation state, which is a very important thing. Transition metals must have, we should not say must, say have, transition metals have variable oxidation state. If we remember, we said potassium or sodium, the S block elements, they had fixed oxidation state, +1 oxidation state in this case. Okay, so here transition metals is variable oxidation state, whereas we do get S block elements, they have 1 oxidation state, no variable oxidation state. This is one sharp difference between S block, P block, and transition elements. Okay, can you see matter? Because there are properties fundamental. Properties are fundamental properties of transition metals, not only to life, but also to modern technology. You remember that we will be using transition metals in modern technology. And as I said a few minutes ago, that for life, the hemoglobin, complexes of hemoglobin, we need that. And therefore, and now I say, why scandium and zinc are not treated as transition elements? Why? Well, if we look to the electronic configuration of scandium, we can have scandium 3 ion, only 1 oxidation state. And if it's scandium 3 ions, then we do not have any electrons in 3D subshell. Okay? So electronic configuration of zinc, if we go to zinc, you see, then we have zinc 2 oxidation state. Zinc has only 1 oxidation state, and that is 2. And that is complete 3D subshell. So as a matter of fact, we can define these 3D elements saying that they are transition elements if they have a partially filled d orbital or full filled d orbitals. Okay, so that's what we have to remember before going further. And you see, the metal look like this. Chromium is this, whereas manganese is black. This is iron. This is cobalt, nickel, copper, zinc. This is the physical properties, the color you see, and the metallic form of the element. Okay, we go to the next slide. Well, we have been discussing also about ionization energy, atomic number. How ionization vary with atomic number. So here we have taken only scandium to zinc. You see, almost same ionization energy for these 10 elements. First ionization, almost same. A very slow and steady rise in ionization energy for this first ionization energy. Remember, we have also discussed about second ionization energy, third ionization energy. You see, we are getting a rise and then a trough, and again and then a trough. And this is because of partially filled, half filled electronic configuration, and this is full filled electronic configuration. So partially half filled electronic configuration and full filled electronic configuration brings this more stable element, and that's why this graph is like this. And this you see also here in manganese and iron and third ionization energy. So we know about the ionization energy and then of these transition elements, especially these transition elements, and then we can predict many properties of these 3D elements of transition elements. Okay. Another one is very important that we have oxidation state of transition elements with Scandinavium to zinc, we have shown here, and the very common oxidation state of these elements and a few of its compounds we show in this figure. You see that here, Scandinavium has only one oxidation state and zinc only one oxidation state. The rest, all of the elements in this period are having different oxidation state, and the blue marked oxidation states are more stable than the other oxidation state. So, for example, here you see manganese has got oxidation state +7, +6. +7 is more stable than +6, +4 than +2, +4 is more stable than +3. So we have variable oxidation state of this. This is a very important property of transition metals. Very important property of this. Okay. Let's go to here. We have discussed this also, and we also show this. We can have one, we can discuss about this one, you see. So one of the most attractive and effective demonstration can be the range of oxidation state of vanadium. Or we can take a solution of ammonium vanadium, ammonium vanadate 5, and shake with dilute sulfuric acid with zinc. What happened then? Before adding zinc, we get this reaction. Before adding the sulfuric acid and this vanadate ion reacts together, and then we get this ion and water. You see. Well, this is yellow. Then this one is yellow. This vanadic ion is yellow in color. When we have acid, and then we get this ion, which is reduced first to blue oxo-vanadium 5 ions, and then this oxo-vanadium 5 then goes to green vanadium 3 ions, you see. And then the last and final one is vanadium 2. Zinc is a reducing agent here. So here we have I show you an example of transition elements having different colors due to different oxidation state. Okay, so again I'm coming back to the color of this. This how it happens by absorbing some of the radiation in the visible region of the electromagnetic radiation. And what is the wavelength of this visible radiation? 400 nanometer to 700 nanometer. When light hits a substance with transition elements, what happens? It's for all substances. It's absorbed. A part is absorbed. A part is transmitted and a part is usually reflected. If all the light is absorbed, what happens? The substance looks black. If all the light is reflected, substance look white. If very little light is absorbed and all the radiation of the visible region of the electron spectrum are transmitted equally, the substance is almost colorless like water. However, many compounds, particularly those of transition metals, absorb radiation in only certain areas of visible spectrum. This means that substance take on the color of the light that they transmit or reflect. Here you see, if we take this complementary chart showing complementary colors, if we go to this color of the light absorbed, if it were absorbed violet color, we see it greenish yellow. Complementary color of the substance there. Well, it is blue in this range, we see it orange. Similarly, up to 700 nanometer, the chart shows if the color is absorbed, this red, we will see blue, green to green color. And why this color is coming up? You know, we talked about d orbitals. We know there are 5 d orbitals, and they do have different shapes. That's what we discussed in atomic structure when we discuss atomic structure. Okay, this is an example of a copper 2 ion. The d orbitals have electrons like this, and they are in same energy level. But when the ion, a d block element, is surrounded by other ions, for example, let's say aqueous ion, then these 5 d orbitals get splitted. This is the lower energy one, and this is the higher energy one. When it jumps from here to here, we see the color of the compound. This is how we have. But look now, if we have 10 electron here, and then we do not have any possibility of jumping from here to this unfilled here orbital, and therefore we do not see any color. In the case of zinc, zinc compound do not show you any color. Okay, so that is what we said. If all the d orbitals are full or empty, there is no possibilities of electronic transition, and thereby do not get any color of these compounds. For example, scandium compounds or zinc compounds, you do not see any color. Well, now we are talking about structure of this transition elements. We do have 2 types of structure, closed spec structure. And in general, we say closed spec structure. These most transition elements have closed spec structure. There are 2 main types of closed spec structure. One is hexagonal closed spec structure. If we arrange a layer of A, let's say a sphere of this layer of A, and then top of this, if it is another arrangement, this is layer B, and then the third one, if it becomes again A type, exactly from first one like first one, and then the fourth one becomes exactly like B, that is the second layer. So we have AB, and if we continue on infinitely, then this sort of arrangement, we call it hexagonal closed specking. And similarly, if we have arranging this sphere and closed specking, we want to do this, we will see that there are another possibilities of arrangement ABC, that means A and then B and then C, 3 layers, and then fourth layer is like exactly like A, and fifth layer like B, and sixth layer is like C. And that what we call cubic closed spec structure. So these 2 type of closed specking we see in transition metals. Okay, next one, that this is, as it is a closed spec atomic arrangement, and atomic radii is also nuclear charge is a little larger. This dual effect, close packing and small atomic radii, results strong metallic bonding. We discussed also about metallic bonding. So if it is a strong metallic bonding, what we expect? We expect higher melting temperature, higher boiling temperature, higher densities, and higher tensile strength, etc. You see. So because of these properties, what you get, we see that transition metals are much less reactive than S block metals or P block metals, or etc. So if we consider the electrode potential of this vanadium to copper, we say that we expect that it should react with dilute strong acids, such as 1 molar dilute hydrochloric acid. But in practice, what we see, it is not that, because the metal has a layer of oxide, unreactive layer of oxides. Just it comes up that the layer in the metal becomes an oxide layer, and therefore it does not easily react by a strong acid, and this is also a protective layer which you call non-rusting metal, owing to chromium oxide. Here we can see that some of the colored compounds of transition metals, we also call them coordination compounds. Do not remember that either you call it coordination compounds and transition metals. Even in some cases we call complex compounds. So there are a branch of chemistry which deals with complex chemistry or coordination compounds chemistry. So transition metal can have coordination compound. We will talk it later, and you see that we talked about half-filled and full-filled desorption. What happens the melting point temperature that you can see that it rises and then fall and then again rises and then fall, and that what is due to half-filled and full-filled desorptions. Up to this, we will discuss, and we take a few more slides on transition metals showing the complex compounds or coordination compounds and their effect, their shapes, and their uses. We will discuss in the next lecture, and that is 38th lecture. Up to this, thank you very much for attending this lecture. I hope you enjoyed it. Thank you. We will meet again, hopefully, in the next lecture on transition metals. Thank you very much.